It's my pleasure today to introduce Francesco Vaccarino, who will be telling us about parallel decomposition of persistence modules through interval bases.
Okay, thank you. Welcome everybody. First of all, let me thank the organizers of this fantastic stream of seminars that bring our own, let me say, warm during this tough period of separation. And today I would like to talk, as Henry has just told, about parallel decomposition of persistent module for interval basis. This is a new paper we put on archive some weeks ago, maybe 1 month, I don't remember. I will give you the link after. And this is a joint work with a bunch of people from our group in Torino. So Alessandro De Gregorio, Marco Guerra, Sara Scaramuccia, and Francesco Vaccarino. Alessandro De Gregorio has just defended his thesis, and now he's a fresh PhD. So let me underline this, and it's very good. So what's the point of this paper? The main message, the main problem? Okay, I think that this first part is quite pleonastic considering the audience, but nevertheless, who knows, maybe there's some interested newcomer might be interested in this. As you well know, there is this tool we work on since almost at this stage 20 years, which is persistent homology, and basically is in this classical and simplest form. The idea is to make a family of simplicial complex grow in fashion of filtration, which means you are practically adding simplices of various kinds in nature on the starting simplicial complex, and it grows towards something. This process usually is motivated and generated by analyzing data at various scales, where the scales are determined by distances, dissimilarity, or as a sublevel set of certain indexing function. In our case, we are working in a classical setting of, if you want to be fancy, if you want to use functors, you are using the setting of so-called compact setting. So, which means that we work with finite dimensional things and with a finite number of changes. And beside that, the process of filtration is discrete, okay? So we are not working in the case in which filtration is over continuous parameter, but actually you have a finite number of changes occurring in this filtration. So as you well know, homology is a functor, so you can fix the degree of the homology K, and given a filtration of simplicial complexes, you obtain a sequence of mappings between the corresponding homology group here, and you can glue all these data together to form what is called, in this case, a simplicial homology module. We will go in detail after. In our work, we try to develop an algorithm to somehow compute a nice generator for this gadget. And the point is that actually, on the opposite of the usual approach restricted to persistent homology, our approach is based on really working on modules, in the sense that we have a sequence like here, M0, this guy, M0, Mi, Mn, and so on, of vector spaces, finite dimensional vector spaces, and the mapping here, phi naught, phi I minus 1, phi I, and the other are linear mapping between these spaces. So you have a sequence of vector spaces with mapping, linear mapping between them. And practically, since these things sprang from generators, from applications, sorry, in reality, you are all very often, not to say always, interesting situation in which this sequence end. So as an example, if you filter on distances and you build Vittori-Rips complex out of a point cloud in a metric space, at certain points you saturate everything, you have connected everything, there's nothing to add, and you stop. So the setting we use is this: at certain point, things stop, and the last one is the null map, sending everything to zero. This is also a technical gadget to manipulate the algebraic datum. So what happened? It happened that the previous structure, practically, if you consider that sequence, so we have our sequence mi phi I, let me say, you can take the direct sum of this mi, and this guy belongs to the category of, sorry, I have always some problem with letters, of fx graded modules, which means practically, if you want to be technical, that you have an endomorph map from f of x to the rings of endomorphism, which is compatible with degree and so on. But all these things boil down in a decomposition. This is M of this module as a graded module over the ring of polynomial, which is a graded ring and which is a principal ideal domain. So very akin to the usual decomposition over PID, you have a decomposition like this, where this is the the torsion part. The torsion part is too thick, torsion. And this is the free in TDA jargon. These are called everlasting cycles. Okay, in case you are working with homology. But I repeat, the idea is that take a sequence of vector space, mapping, connecting them, consider the decomposition, and then here you have an example, a very simple one, in which you see you have R1, R2, 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 R1, and these depicted here, here, and here, and here, are matrices. So everything is given with respect to the canonical basis. And as a result, you have a decomposition like this. You can write down M like a direct sum of two guys that you can represent diagrammatically as pieces of barcode. Let me use that. Okay. So what is interesting is that these sums are all direct, and this is what we are after practically. Indeed, the idea is that we want to find objects, elements, homogeneous in the module M, which generate the module as direct sum of interval modules. Okay, these interval modules are this guy, which are nothing but what we have written here. Okay, the summands here are what is written here. And clearly, dm can be plus infinity, but since we send everything to zero at a certain point, all these are finite intervals. So the point is to find a list of elements homogeneous, such that the cyclic submodule generated by them, I repeat, over the ring of polynomials, okay, are provide the decomposition that we are talking about. So why we need this? There are several reasons. One of them is that for those one working as an example in neuroscience or in material science or in any other applied setting where this persistent homology has been used, have faced it if they are taught really with people, so-called field scientists, people expert in that area. On my side, we have brought some paper. We work on neuroscience, some model of the brain under psilocybin and other things. And one of the problem is that the pipeline of TDA is quite long. And so it's difficult at the end of the story to interpret the result TDA provide in terms of the initial data. One thing that may address this problem is to have explicit generators. So to find really which cycles generate the persistent module, because these cycles sit down in the initial network, as an example, or the initial point cloud. You can see them, okay? This is a tough problem. And also, in our case, is a little bit different from finding what we use as an example for scaffolds or finding minimal cycle. We are not on minimal cycle here. We are only looking for algebraic generators. Not any algebraic generator, but those ones that exactly provide you with this composition as a direct sum of interval submodule. Any questions so far? Is okay? Is everything clear?
So far, so good for me.
Yeah, okay. So don't be shy. If you want to ask something, write in the chat or interrupt me. It's not a problem at all. Anyway, so usually the classical computation, everyone probably knows, but we go through it now, is done in the following way. I simply read what is written here. You consider a filtration given by the addition of one simplex at each step, and then you generate a sequence of simplices and consider the boundary matrix where the hive column is the boundary of the simplex Si from the list, expressing the basis given by the sequence of simplices. And then you can reduce by column this matrix and rewrite this in the following way. So R equal to D times V, and the columns of V corresponding to 0 columns of R in induced generator of persistent homology model. This is the clever mechanism behind the classical algorithm to compute persistent homology. And so just to give an example, consider here the following situation. Let me only stress that, let me put a different color, okay? Here you see, we have as triangle, we have this one and this one that corresponds to this and the one outside, okay? This is also depicted here, you see, there are these two triangles, okay? Obviously, you can write simplices also in other ways, but we want to use this one. Okay? So D is the matrix encoding the boundary. So very simple. Let's look as an example. Here you have 0, 2. Correspond exactly to 0 and 2. Okay, nothing strange. And 0, 1, 3. Guess what? You have its edges. Okay, 0, 1, 1, 3, 0, 3. Okay, this is the boundary matrix. So this is the matrix R you obtain from the decomposition. And you see here you have these columns are 0. And this is the matrix V. And the columns here, you see 0, 2, and 2, 3 correspond to the red generator there, 0, 2, and 2, 3. And so on. And again, here is the same mechanism. It's the comparison of the two matrices. So, but the point is this, I mean, I leave you this calculation. I don't want to repeat all the calculation here, but simply you have these two matrices and you can consider the two steps and their corresponding decomposition here. I want to go straight to the point. The point is this. The point is that in this example, you have the classical algorithm will produce H1 and H2, and it holds that H1 of K0 is H1 generated by H1, H2, and H1 of K1 is generated by H, and so you have these two coincide under the map phi star inducing. So the point is that the interval module generated by H1, the subgroup, the cyclic submodule, is not in direct sum with H2. So the two generators are okay, but what they produce is not the decomposition we have seen at the first step. Okay. So because what happened is something like this. Here you have something more visual, probably you can see. Here we have two generators for this torus, piece of torus, And you have on this half torus that if you filter along the parameter, at a certain point, the two cycles will coincide. So you have a situation like this. Graphically, is like this. And algebraically, is like the one before. Practically, you have two things going in the same. This is not what we want to have. This is practically the interval generated by this, and this is the interval generated by the other. At a certain point, they collide, and they are not separated. What we want to have is something not like this, so something which linear relation do not appear, but somehow the generators travel along the filtration without colliding. Okay. I want to underline that these things that we are showing now with, simplices and so on, are just given to, to give you some insight on the mechanism. But what we are going to talk about will be completely independent of using simplices. We don't need simplices. We don't need a filtration. We need only a module, a persistent module. Okay. This is, and so it doesn't matter if it is also the homology of some filtration, you will get a system of nice generator for persistent homology. So let's go back to the concept we have talked a little bit about before. So given a persistent module, a finite family of elements, homogeneous, as an interval basis for M, if and only if the direct sum of the cyclic module generated by them is equal to the entire module. So we are asking that they generate the module, but also that the module generated by them are indirect sum, so pairwise independent. So if you remember the scheme before, the idea is to find two generators such that you have this situation and not this one. You don't want these to coincide with the other after some step. You want them go on until they go. They can become zero, they can disappear, but they will not go. You don't have practically that there is something like phi of W for two of the generators. You don't have this, unless they are both going to zero. Okay, so this is the problem. And okay, and this is the same, so it is a copy. Okay, okay, so we want to do this. And how to do that? Okay, let me say, everything here is not transcendental. There are not super sophisticated techniques. It is only a clever application of some nice observations. So the first one is that when you have a sequence like this, there is a flag of vector spaces. So that the kernel of phi is containing the kernel of phi I plus 1 composed with phi, and so on, until you arrive to the end and you get the mi, because everything goes to 0. So you can consider this flag, and you give a definition of a basis of mi, one of the step in the filtration. Let me use this terminology, or one of the homogeneous summand of the persistent module. A basis is adapted to the flag if for every vector there is an intersect Sj such that what happened? You have that after Sj minus 1 step, you get 0, different from 0, and the step after you get 0. You have this, but before is always less than 0. So this is adapted to the flag. And the idea now is to use this kind of adapted stuff to find the generator. practically, then I explain you, but I want to show you immediately how it works, because in my opinion, it's simpler. Okay, this is a very super simple example. So let's take a sequence of vector spaces whose dimension is equal increasing by 1. So one is F2, F3, F4, F5. And the map is simply the embedding of M1 into M2, into M3, and so on. Okay, so you see from the matrices. I'm assuming here we have fixed the classical canonical basis and so on. Our algorithm will construct a system of generators which are exactly what you expect to have. So you see, here is the 2 from M1. And then is the one you add. And then you add another one, and then you add another one, and then you add another one. So clearly, I mean, this is completely trivial. This is not, this is something we have used as an example to verify if the algorithm was working correctly with a sort of litmus paper or null model, okay? But you have to think that what you get is something like this. So you have a system in which each time you are adding something that is not coming from before and such that is not colliding with the one that are already there. So as an example here is less trivial, same size, but the same way you get a system of generator, what we have said before, so interval basis. And these guys here, these two, and then these, and this, and this, and this, generate interval modules that are in a direct sum and completely fulfill the direct sum of M1 plus M2 and 3 and 4 and 5. So this is the what should come out. How to do this? Okay, first of all, we start, so the input is the persistent module. And practically, since everything is finite, we can choose bases and matrices representing the mapping. So practically here, you already have the map between modules. So as a typical example, you can think about, you already have in your hand, or always when you do TDA, are the inclusion of the chain group. This is a very trivial example that you can consider, but you can also consider sequences in which you have mapping without having any further information about where this mapping came from. So it's not necessary, I repeat, to work in the simplicial homology context. Simply, you have a sequence of vector spaces and mapping, and you build a structure of module, graded module over the ring of polynomials. Okay, so the main idea is to make a iterative process in which at each step we add things to the one that we have previously constructed according to this strategy which is explained here. Okay, so first of all, you compute an adapted basis of M0. And you add the vector to the adapted basis. This is the 0 step to the set empty set, okay? Because you have nothing when you start. Notice that as I have written here, if I is 0, phi minus 1 has to be taken to be 0. Okay, so you think that before the first summand of your module, there's nothing. Okay, it is 0. Okay. Then for a record for each vector, its index, so the number for which, if you remember, it holds that it becomes 0. So practically, you consider, if you want to consider this in terms of module or group theory, this is simply the order of the element as a k of x module. Okay, so if I multiply times x via the map phi. This is when the first place where the object disappears. And clearly, this is at most n because we have phi n equal to 0. Okay. So practically, this vector correspond to elements of the persistent diagram starting from the 0 position. Typically, when you compute H0, you start with points and you have a lot of these guys, and then they disappear as long as the various connected components grow and glue together. Then, what happened at the high step? You compute an adapted basis of MI. So you compute a basis made of elements that, as before, are coherent with the flag of kernels. And then you compute a basis of the image of the map. And then you complete this basis to a basis of MI, introducing the vector that you have found here in the order given by their indices. Okay, so practically you have the basis U, and then you add things like J1I, VJ2 I, VJT I, with the condition that SJK is less or equal than SJ. H if K is less or equal than H. Okay, actually is less here and here less or equal. Okay, this one. And so you have computed your adapted basis. Then you take the image of the element before, you take this one linearly independent, then by basis completion, standard tool, you add this vector that you know when they disappear, okay? And you know also that they are, what happened? I've done something strange. Oh, wait, okay. Okay, and also you know that they are linearly independent and linearly independent from the previous one. And now you go on, you add the vector to complete the basis and state their indices. So this is the mechanism practically. So you get generators from the previous I, U is the basis, you take the adapted basis, and then you reduce with U and you take the union, this is the new basis. And this produces a list of interval modules that are in a direct, that you can put in, sum is direct and homogeneous, and such that at the end cover the entire module. This is the claim. I mean, now we see the proof. So, or at least the theorem. Here you have another example similar to the one that we have seen before. Step one, an adapted basis of is 1 and 1, since N1 is the kernel 1, 4, and the image of phi 0 is 0. So the first one is the identity is 1. Then, and we add the point 1, 4 to the persistent diagram, because here we know when it died, okay? So you compute the adapted basis for M2, and the image of phi1 is this, and then you take the image and you add, as an example, the vector V1 minus 1 from M2 from here, with persistent pair 2, 4. Third step, an adapted basis of M3 is 1, and the image of C2 is the entire module, so we do not add any vector. So practically, at the end, we have what? We have obtained this guy here, and the other guy here, and the other guy there. Okay? So for every MI, an adapted basis can be constructed such that it contains the subset VIM that is a basis of the image of the previous map. And we define VI birth equal to VI minus the VI coming from the previous module. So practically, you have that you have the map from I minus 1 to I. Here, you have the part of the adapted basis that arrived from this, and here you have a new part which you call V I birth. So are the new one generated at this point. And so you can use also, you can consider this function mapping the indexes. So you can order this vector, and this is the mechanism. So here, I don't do the proof here because there are only 5 minutes, but it's on the paper. The point is this: first, for any I less than j, the map phi j restriction of the map phi j to the subspace generated by V in Vi with j greater than the index greater than j is an injection. So vector in the adapted basis remain independent through the structure map. And for any I less than j, you have that phi ij birth intersected with phi I in the same image is 0. So the image of the linear span of two subsets are always in the of the two linear span are always in direct sum. So practically you obtain what I showed you before here. And so to recap, we have an algorithm which, doing some simple observation, is able to extract generators of interval modules so that you can write the persistent module at direct sum of these. And this is independent from having methods like filtration, complexes, simplices, and things like that. It's purely algebraic, linear algebra, let me say. What happened? As an application, consider this. Now we have a persistent module. Now we have more than a persistent module, let me say. We have a filtration, or we have a mapping of chain complexes, okay? So now you know that given a chain complex, one thing that I have to stress here is the following. Now F is equal to R. We are over the real. Practically, I want to take advantage of the Hodge decomposition and representation, the identification of homology group with harmonics, so with the kernel of the Laplacian. You know that the Hodge or combinatorial Laplacian is the map from CK to CK given by this. As you know, this is the so-called lower Laplacian, and this is the upper Laplacian, and there are tons of papers on these things under any kind of perspective. What is well known is that the space of harmonics, the kernel there, provide a decomposition of CK as the image of boundary direct sum, and this is orthogonal with HK plus the image of the boundary. Okay. You can write this way. You can write you can write this in this is in a homological fashion, but you can write co-homological if you like. In any case, it's not complicated to show that if you consider a chain map and the natural inclusion provided by this decomposition and the orthogonal projection from CK to HK, then you can construct a map for each K, f at K, which is the composition of inclusions, okay? So you have the inclusion in CK, then you go in DK, and then you apply pi K here, FK, and so this map HK, so HK. And this is a nice map. And it is the same as the map between the homology group. Okay, but it's written all in terms of simplices or chains, and not in terms of residual classes with respect to the boundaries. And this is what we are interested in, having a description of homology, computational description, which is straight in terms of chains and not in terms of representative, which, as you know, is a big trouble. You have problem with minimal length representative, which representative to be chosen. Finding this representative is at least for k greater than 2 is NPR. So I mean, is a is very tough. And so in this case, we work directly with chain, and we build a persistent module, which is the usual persistence, but is simply written in terms of map between harmonics via this orthogonal decomposition. In this case, as is written here, you have that our algorithm will provide a direct way of computing persistent homology, at least in the real case, directly without working with residual classes or with other systems, so it's direct. Okay, this is a possible application. Okay, just to conclude, we have new algorithm to compute persistent from persistent module rather than a filtered chain complex. So we start directly with the persistent module, whatever it came from. Not only persistent module made of homology groups, as I said, not only persistent module made of homology group with inclusion induced map. We don't need inclusion. And distribute implementation feasible over each grade in the persistent module. So you can distribute the computation. You first compute all the homology group, as an example, in the real case. You can compute all the homology group as kernel of Laplacians. And since the map F are already there, this one, you have all the ingredients to write down explicitly a persistent module was terms are the harmonics, and you have the maps, and then you can use the algorithm to directly compute persistence. But you don't need inclusions. You have no need to have inclusions. Okay, this is important. You have two versions practically. If you go in the paper, you will see the detail. General coefficient filled, and real coefficient. Real coefficient is take advantage of the Hodge decomposition and the advantage of simplifying the procedure by using singular value decomposition. Because you're over real, you can use singular value decomposition to simplify the computation. And interval basis, these new kind of generators compatible with the structural theorem. Classical generators do not generate the persistent diagram for structure map. This is needed from associated with persistent diagram. The interval basis generate the persistent diagram through the structure map, and interval basis correspond to a set of homogeneous generators for each interval module in the interval decomposition of the persistent module. So this is what we have done so far on this theme. Clearly, there are other things to be done. And first of all, not necessarily including inducing persistent module made by homology group. We won't try to exploit this more. The part on harmonic, there are many people now working on this. There are many works around. Some are quoted at the, anyway, they are referenced in the paper. We overcome the non-functionality of harmonics by writing directly the maps. And one thing we want to go on is these things on persistent Laplacian by Memundo, Memoli, Zhenxiao Wang, and Yuzu Wang. And the other future direction, what about not-oriented AN quivers? I mean, so far our persistent module is and the interval decomposition abstractly work by work very old, really work of, as an example, Hans-Peter Kraft, Abeasis, Procesi, De Concini, and so on. There are many papers in the 70s and 80s on the decomposition in intervals of module of type AN, and not only. And so one thing is to try to understand the structure of this in terms of quivers representation, and especially on general quivers. Carlson recently published a paper with result not so comparable, but not exactly the same with us. But he also work is very much addressed toward general queries. We also want to try to do this somehow. And so thank you for all your attention. And here there's some references.
Thank you very much. So before we get to questions, let's briefly unmute ourselves and applaud for the speaker. Questions for Francesco?
I've got one if you're able to hear me. Yeah. So in the first part of your talk, can you, or this is Brad Nelson, sorry, just to say hi.
Yeah, I saw the name.
Yeah. Yeah. So in the first part of your talk, how is this, or how would you distinguish this between the algorithm of Carlson and De Silva that was given in their original paper on zigzag homology in terms of right filtrations? Because it seems very similar. And I'm just curious, like, what you would say the key difference is.
So I don't know if I have got what you talk about. Is this one, which is here? Which algorithm you are talking about?
Sorry, I muted myself.
So you say the first
right. So like the idea of dealing with, let's say, arbitrary maps, like in the persistence module, right? So not necessarily from chain complexes, right? You know, and at least in TDA, this is, I would say it kind of like the paper on zigzag homology by Gunnar Carlson, Vin De Silva on zigzag persistence was, which related this to type A and quiver representations, was really like the first general look at this, right? Where you can deal with arbitrary induced maps, right? And they give an algebraic algorithm in terms of what they call right filtrations, right? Where you essentially, you know, keep track of how vectors are appearing and entering the kernel, right?
Yeah.
And from what, so it seems like your algorithm is similar to this, and I'm curious what you would say the key distinction is.
I think the greatest difference I find in is that, if I remember well, I may be wrong, but the biggest difference I see is that in our algorithm we produce generators which provide we produce generators that provide the basis they build. So we can produce their basis, you know, but providing generators. So we are interested in generators as, if you want to be fancy, as a module over the quiver algebra, okay? What they build is an adapted basis, which is not exactly the same we do. We do not simply produce a beautiful basis of the module as they do. We produce a system of generators that, as a byproduct, provide the basis they provide. So we are able to build their basis, but providing generators. This is the difference, in my opinion.
So if they had provided the explicit change of basis, would this, or I don't know, would this do the same thing if they had written down the change of basis?
No, but they produce a coherent basis in a way which is not the same we do. As I told, I want to repeat, what we build are generators of this direct sum of cyclic modules, okay? As a byproduct, you produce this sequence of coherent bases from this one, if I have understood. Furthermore, they parallelize divide and conquer and not on the steps. So there are two different approaches. But the result is very similar. I agree with you. It would be very interesting to compare in more detail. Definitely.
Oh, yeah. I mean, maybe we should discuss later. But yeah. So the paper you cite at the end, that was the one from 2 years ago. And actually, I'm the last author on that. I'm the final author on that. The final name on that. But that algorithm is different than the one I'm referring to, which is the original algorithm for zigzag persistence.
You are talking about the one of zigzag of Carlson, maybe, I don't remember, with Zomorodian.
And De Silva. In 2008. Yeah, so in 2008.
I thank you for pointing out this. This is some sort of a very comparable approach, but I think our is a little bit different from them, because we stick more on the constructing generators. as a module of the derivative polynomial. I don't know if our approach can be extended to general, as an example, posets, incidence algebra, things like this. I don't think so for theoretical reason, because it's, if it's not a Dinkin diagram, you know that there is no discrete invariant complete, so maybe it's not possible to write the module in that way, because the algebra is no longer a PID, so it's much more complicated, okay?
Mm-hmm. Yeah, all right, thank you.
Thank you.
Other questions? In the case of real coefficients, I was wondering if you could explain again how you leverage the singular value decomposition.
Yes. Oh, good question. I don't remember the detail, to be sincere.
No problem. I can check.
No, because is there something about the computation of the adapted basis? You know, in that case, if you have singular value decomposition, it's easier to do that. Because you remember the adapted bases are those things that are coherent with the nested sequence of kernels of the compositions, okay? And using the singular value on the composition is easier to do that.
Thanks.
Yeah. You're welcome.
More questions or comments? Or let me at least. Oh, go ahead, Brad.
Sorry, I can ask questions all day, but I'll try to keep it. But one question I have about the real value problem. So like, you know, if you go back in the numerical analysis, well, so it's well known that computing the Jordan normal form over the real, like using floating point arithmetic, is not stable, right? And there's a viewpoint on, you know, doing this sort of computation where you're essentially computing the Jordan normal form of a matrix when you compute persistent homology, especially in this way. So I'm curious, like, have you run into stability issues when you in your your implementation, or I don't know if you've implemented this, but if you run into stability issues?
No, so far we didn't apply yet to let me say real cases with a lot of numbers checking stability issues. Is it correct what you said? Because practically this kind of basis is a sort of decomposition in a direct sum of the you know, it's exactly Jordan form. You have the nilpotent element and the semi-simple part. This is the game. And I know that there are problems in stability, but to be sincere, we didn't check yet because we finished this paper really 1 month ago. We put out the algorithm, and now we will apply to several things, and we want to try to use it and to check it in detail. I have one of my graduate PhD student that is working also on implementing it with an optimized code. So then we try to understand it. Thanks for again for pointing also this aspect.
Very nice. Well, let's at least end the recorded portion here. So thanks again, Francesco, for the fantastic talk, and thanks to the audience for your time and attention.
Grazie a tutti.